Yeah, so I work for the V8 team in Munich, and well, V8 is a JavaScript engine of Chrome and Node.js and some other embedders. And V8, as of last year, has 2 new components, an interpreter and a new compiler. And so today I'm going to talk about the compiler. And Turbofan, like the most obvious difference of this new compiler is that it's a C of Nodes compiler, whereas the old one, Crankshaft, was a kind of CFG SSA compiler. And so we have a simple program. It's super simplified. And the CFG in SSA form looks like that. So, I mean, the SSA property is that you only use variables from preceding blocks, like values, and instructions are the same. It's obviously possible to reconstruct this schedule. I omitted the dependency between the phi and the loop, just for readability. And then there's also this load and store, and now if you're naive, you could try it like that, but this doesn't work. Because now the load and the store could be actually scheduled in the false block, and nothing tells us where to schedule the load and the store. So what you do need is you need some kind of effect, like we call it the effect chain. You could also say it's the state of the heap that flows through this program. In a sense, SSA programs are kind of functional. Everything is a value, so also the heap has to be a value. I think that's the easiest explanation for why we need this effect chain. Yeah. So C of Nodes is kind of a controversial topic. It's yeah, it's like the most obvious thing. It's complicated. Like it's not obvious what these graphs mean, and if you work on it, it still doesn't get obvious. And yeah, so then, like, if you do C of Nodes, you have to represent all the dependencies of values and computations and effects in the graph. If you don't, then you get a completely scrambled schedule and weird bugs. If you have a CFG, yes?
Are you telling me that you don't have anything in the scheduler that actually does implicit scheduling?
No, I think everything is in the graph. But like we use the effect chain heavily, so most of the things where we care are in the effect chain.
Because as far as I repeat the question to you, as
Ah.
far as I remember, in the C2 scheduler, there are still some things that the scheduler actually tries to pair together to get scheduling to be better. It's really hard to express everything in like the explicit dependencies.
Yeah. No, we do have some kind of marking on the effect chain where nodes have to stay together when we lower allocations. But apart from that, there's nothing really. Okay, so the disadvantage is you have to track all the dependencies, but probably you want to do that anyway because otherwise you can't reschedule. Like in some sense, C of Nodes as an unscheduled IR, the only difference is that you throw away the schedule. You could do kind of the same things you do in C of Nodes in a CFG if you had all the dependencies and then you forgot about the schedule. Yeah. So one attractive thing about C of Nodes is that you can just take a node or a bunch of nodes and replace them with some other nodes, and you don't have to care where they are scheduled. Well, you don't have a chance to care anyway. But on the other hand, if you need a schedule, you have to compute it. And like V8 is a JIT engine, and we have to be fast, like JavaScript code is loaded all the time. So compilation time is somewhat important, and then you can't just recompute schedules all the time. So our pipeline has 2 scheduling phases, one in the middle for low rings and one in the end for the actual code gen. And we couldn't really afford more schedules. So if you want to write an optimization and you would like to have a schedule, well, usually in our case, you don't. If you have a CFG, then you always maintain a schedule, so you have it there at least. Yeah, so it all depends a lot on the scheduler. Like if you have the perfect scheduler that computes the perfect schedule, then C of nodes is perfect because, yeah. On the other hand, schedulers are not perfect, and so the scheduler can also screw you up. And since you don't maintain the original schedule, you might get worse than what the programmer wrote. Like if you instead were on a CFG, then you could do local improvements where you're really sure that you do improve something, whereas in C of nodes, you have thrown it away already. So we reduce this C of nodes with a DFS from the end, so we only see reachable nodes, which is kind of nice. But on the other hand, this reduction is expensive, and these DFSs all the time make the new compiler much slower than the old one in terms of execution speed. Part of the reason is also that if you do this DFS, then you get the nodes kind of in a random order, and sometimes you don't want that, then you have to do extra logic to get them in the right order. Then in C of nodes, it's really hard to do lowerings if you want to replace a pure node with some that has effect or control or something like that. We actually do that, like we have floating control where we suddenly plug a small subgraph into the middle and the scheduler handles it, which is complex and not ideal. Yeah, I don't really have an answer there. And one obvious difference is if you do CFG, then you can do reductions on basic blocks, like you do one basic block at a time. And in C of nodes, this is harder because you don't have these basic blocks. So you would have to schedule to just process one basic block at a time. And this makes, as we will see later, optimizations harder to be efficient, because sometimes you really have state in your analysis that's just relevant for this basic block. Now, if your reduction happens to kind of visit different basic blocks in random orders, then you have to maintain all of the state. Okay, so now for the real topic of this talk, it is escape analysis, which we re-implemented last year. So escape analysis is kind of classic compiler optimization that removes object allocations. And now there are different versions of escape analysis, and what it exactly means, like for us it means removing the allocations completely. In the Java community, there's also escape analysis which removes heap with stack allocations. We don't do that. Yeah, so in this example, this is JavaScript. Like small program, you have an absolute value function which computes the absolute value of a vector, and now you might express the diagonal function using this absolute value function, and then you will allocate a temporary object. And of course, you didn't want that. So this example is like the most common case of escape analysis is between the boundary of functions, where you allocate temporary objects. Like on the Octane benchmark, which is kind of relevant for us, there's this ray trace benchmark, which does exactly this kind of vector arithmetic all the time. And there, like escape analysis makes it 2x faster, just because you save the allocations. So yes, we have to remove this allocation. How can we do that? Well, first of all, we have to inline. As always, inlining starts all the optimization. So once we inline this second function, then it's kind of simple. You replace the field loads. You kind of do load elimination. And if you did load elimination, then this temporary object got useless. It's not referenced at all, so it's not surprising that we can throw it away. So this is the easiest case of escape analysis. And in practice, it's a lot harder. One reason is that load elimination is not enough, at least not in this form. Like in V8, we have a very simple load elimination that doesn't introduce files. In general, you want to replace the object fields with local variables. So for example, in this case, The A field can be replaced with a local variable, and then all the accesses and writes and loads happen from the local variable. So in our intermediate representation, a local variable is a bunch of phi nodes, essentially. So escape analysis has to introduce phi nodes on the fly. Then we also want to support nested objects. So you have to track through several layers of indirection to support that. And also, if you store an object into another object, it escapes if the outer object escapes. If you pass your local object, you just allocate it to some other function, then it escapes the current scope, and so we have to materialize it. We can't dematerialize it. But this is only one of the many cases why you have to do that. Like, I think it's a bit of a misnomer for us, because if you do this stack allocation kind of escape analysis, then it's pretty much about escaping. But since we don't stack allocate, there are many more cases where we have to materialize the object. For example, index accesses. If you don't have memory, you can't do an index access. And another case, well, you can do an index access if it's a constant offset. But with a variable offset, there's just no way to lower this to machine registers, for example. And then also, which is a bit harder to explain, if you use the identity of objects, we can't really, well, we could perhaps, but it's not obvious how to lower that. So we want to replace all the temporary objects with local variables. And in our version of escape analysis, there is no runtime representation of the identity of an object. So as soon as you do something that depends on the runtime on the identity, like in this case, we have two objects, and we choose one of them to store into. This kind of corresponds to choosing which local variable you want to store to, but without control flow. Now, if you wanted to compile that and remove the objects, you would need to kind of choose a machine register without having a branch. This doesn't work. If we did stack allocation, then we could do that. But stack allocation is hard for us, especially since we would have to move objects off the stack when we deoptimize. Because we can deoptimize at any time, which is the next topic. So, suppose you have this JavaScript. Now, if this was Java, then you would be fine. I mean, nothing really happens here. You have a function that does nothing. You allocate a temporary object. You compute +1, and then you call this function. Like, you would expect that you can compile that to something like that. Well, you can't, because +1 in JavaScript can have side effects. So, okay, then you say, okay, +1 has side effects, whatever. Put it there. But that's not enough, because this +1 can actually replace harmless with something else while you execute it. So there is no way how you could have this function check before you execute it that everything is fine, then start executing it. And then you escape analyze away this temporary object. But at the point where you execute +1, suddenly your assumptions break. And this temporary object has to be materialized, because this is the example. So we can call foo with an object instead of a number. And now this object has a value of method, which is called implicitly by the to-number conversion. And all it does is replace the harmless function with an evil function. And the evil function takes its arguments and escapes it to a global variable. So, yeah, it's something you would do. So what can we do? We want to do escape analysis. We have no option, but we have to jump at the moment where this happens from the optimized code to some unoptimized version. So this is essentially what we compile it to. We check that everything is fine, like we executed this function a few times, we always saw a number, no weird side effects happened. So we speculate on x really being a number, and if it's not a number, at the moment where we would do +1, we deoptimize and jump back to the unoptimized version. Now, in the case of escape analysis, you can't just jump back, you also have to allocate the objects that you didn't allocate. So what we have to do is we have to track all the escape analyzed objects and their current state just to materialize them right in the right moment. And this is also the reason why kind of like stack allocating or something like this is hard, because you would have to move the object off the stack. Okay, so now I have an actual example of the algorithm as it's implemented now. I did not use our intermediate representation because it's just not too readable on a slide. These nodes quickly get unreadable. Also, if you debug and you have 1,000 nodes, it's kind of annoying. Like, from a practical perspective, CFG is a lot more compact than C of nodes. It's kind of hard to visualize it. You kind of would want to compute a schedule just to look at it.
Still don't understand why you picked it. There seems to be so many problems, both the visualization, footprint, and your negative list was longer than your positive list.
Well, yeah, I don't know.
What did it make so much easier that it was totally worth it? You don't know yet.
Yeah, we don't know if it's really worth it. Like,
That's what our big guys are doing anyways.
Okay, so for escape analysis, we need to keep track of all the objects which we want to escape analyze away, and we need to keep track of their fields. Now, keeping track of their fields means mapping them to local variables. And so this is what we do. When we see an object allocation, we allocate some kind of virtual object, which is for the compiler a global representation of the shape of the object, its offsets, and its fields. And the fields we map directly to something like local variables. Well, actually, these local variables are just a side table that map them to their current value. So the virtual objects are global for the complete analysis, whereas the current value of the variables is something we have to keep track of. So in C of nodes, this means we kind of have to attach this current state of the newly introduced variables to each effectful node. Yes. So then, if we see another allocation, we allocate another virtual object, create new local variables for it, and continue. If we see an assignment, a store to an offset, then we can look up, like A is the first virtual object at offset 24 is something that's described by a variable AX, and the current value is null, and we replace it with B. So stores, kind of simple, you just have to update the current variable. Now, if you have like two dereferences, two field accesses, then the first one is a load, the second one is a store. So first we have to handle load as before. A is the first virtual object, the current value is B. So A.x is B, B is the second virtual object. And the Y offset of this one is the local variable var bi. And it used to be 5, and now it's I. Since we are in SSA, we can just refer to dominating instructions directly. And now we have a control flow, merge, where we introduce a phi node. it was really helpful to structure it like that, to have this kind of abstraction of local variables. In our previous implementation, we didn't have that, and it was kind of confusing. And now we have a function call, and from the preceding slides, you should be worried about function calls. And so at this point, we might deoptimize, because when we call a function, we never know what happens. So we have to remember deoptimization data. And this is essentially a dump of the current state we maintained. So for each virtual object, we have kind of representation of the virtual object, and the fields are based on the current value of the variables. And this small subgraph on the lower left, gets essentially inserted into the sea of nodes SSA form. And we might have several of them, and they can be nested, and they can even be cyclic. Because if you, with assignments, you can easily create a cyclic graph. And then the deoptimizer has to build this cyclic graph. And in the end, we can just remove all the allocations, all the assignments to dematerialized objects, or the loads from dematerialized objects with the value of the variable. So this is kind of a happy case. So the example is very artificial. So now I change it a bit. What happens if, like, for example, the inner object escapes? If we just return a.x, then the b object escapes. And if we did the analysis as we did it before, then we only noticed this in the last line. So all we did before is invalid, which means we have to jump back to the beginning and redo everything. And this time, virtual object 2 doesn't exist, and the rest of the analysis proceeds with this information. So at any point in time, we have to be able to redo everything. And this is also the first challenge. Like with simple local optimizations, you can just take the graph, replace some nodes with something else, and you're done. Like a straightforward version of load elimination does that. But here, we really need to finish the analysis before we replace anything, because everything we do depends on that stuff doesn't escape. So we have to separate the analysis phase and the replacement phase into two distinct phases. And first, we record all the information, and then later we replace if we finished, like if we reach a fixed point. Essentially, what I showed you before, this is repeated until we reach a fixed point, until no information changes anymore.
So you would theoretically have additional up to one pass per escaped object in reanalysis, because you could separately detect each escape and have to repeat everything.
Yeah, exactly. Each object can escape only once. So in the worst case, you would notice it exactly in the wrong order and then relook at the function each time. So kind of the worst case complexity is quadratic in this case. Yes?
Could you do the pulse in like the reverse order to like from bottom up?
Well, not really, because you need to really do the analysis, you need the information about all the virtual objects you saw before. And whether something escapes or not very much depends on your current state of your analysis. If you store to an object, then it depends on the current state of this object what escapes. Like, yeah.
But why don't you just materialize an object from this virtual state you collected at the point when you realize that it can escape? At least that's what Graal does.
Yes, we could do that. This would be partial escape analysis.
It will eliminate the need
Yes, yes, but it makes stuff also harder. Like,
Well, some technical limitations on runtime, probably.
no, this is possible. Yeah, I wrote a prototype. It's possible. Yeah, it makes stuff harder also because then you need to keep track of which object is escaping at which point. Like an object can then be dematerialized or materialized at different points. And especially in Sea of Nodes, this is complex because for pure nodes, you don't know when they happen. So if you have a reference equal between two objects and you want to know, are they materialized or dematerialized right now, then you don't know what is right now because the reference equal is not in a fixed position in the effect chain. So Graal actually does it on a scheduled graph escape analysis, as far as I know. And it gets a lot simpler if you do it on a scheduled graph. But for us, we didn't want to do another schedule. Yeah. Which is the other point. Like I showed you this list of variables on the right. And implementing that efficiently is not too easy if you have to copy it for every effectful node in the graph. So there are two options. Like what we tried before is not copying this state too often. Like if you were in CFG, then you would just walk through the basic block and update the structure imperatively, which in principle you can do in Sea of Nodes, but for this you would have to know the basic blocks. And we tried that before, and it's kind of tricky to get it right, to manage the state so that you duplicate only when you need it, kind of implementing copy on write by hand, yeah, was a source of many bugs. So what we do now is we have a purely functional map data structure, which has both the benefits of sharing state and sharing memory, and also the benefit of not having to worry about mutable state inside of the analysis. So we have one map per effectful state, and we copy them when we walk along the effect chain. And if you use a purely functional data structure, we use a hash tree. Then copying is for free because everything is immutable. And updates path copying on the tree, and the tree is of logarithmic depth, so that's also not too expensive. So this way we got back most of the benefits concerning memory and execution time we had before with the manual copying, but it removes a lot of headache. Yes, so in summary, escape analysis avoids allocating temporary objects, and in V8 or in any JavaScript engine, you have to do this in the face of deoptimizations happening almost anywhere, and while the function is executing. The version of escape analysis we do without stack allocations has limits in escaping uses, index, accesses, and whenever you use the object identity. And for this particular optimization, doing it in Sea of Nodes was really a challenge. And I mean, Graal does it in Sea of Nodes, but they do it on a scheduled graph, which kind of doesn't count. Yes, so in this case, DIR probably was the main challenge. And it turns out that purely functional data structures can be really nice if you do compiler analysis, because, well, usually you do a fixed point iteration, and like you have the mathematical model, you have values, and purely functional data structures give you values, and you don't have to worry about state. Yeah, that's it. Questions?
or in JavaScript, you need to deoptimize almost anywhere. You don't have to do something special. More or less, the optimization doesn't affect the fact you need to track, right? If you had only one deoptimization point or 20, you would do pretty much the same state tracking.
Can you repeat the question as well?
Yeah, so the question was if the state tracking is the same if you have little or many deoptimization points. So probably the state tracking is kind of the same. One difference perhaps is that like in JavaScript, you could never have a function without deoptimization points, whereas in Java, I guess that's possible. Yeah, I guess that's the main difference.
Is there a way for me when developing a JavaScript program to profile it to see if I hit very many of the problems in your optimization without knowing about the optimization per se?
Well, there is not really a way. You can easily see which objects are escape analyzed away and which ones are not. I mean, you could look at the optimized code, or yeah, but in general, well, you can check if your program is dominated by allocations somewhat. Like you can just look at how much EC work you have, or we don't have detailed profiling for this now.
Have you tried using escape analysis to guide your inline?
What do you mean?
Do an escape analysis to see which variables escape through calls to other methods, and then use that information to see what methods to inline to be able to escape analysis, or like dematerialize more?
No, we don't. So the question was, do we use escape analysis to guide inlining? And no, we don't. Also because it happens much earlier in the pipeline, and we would need to keep track of that somehow. In general, we inline a lot, so we kind of almost always inline everything where we think it. Like in JavaScript, you almost always benefit from inlining. First of all, because you don't have type signatures on the call sides. So if you just want to pass a float efficiently, you have to inline. So inlining is so beneficial for us that, yeah.
Yeah, but I guess that at some point you end up having to decide which ones to inline, because you can't just inline everything because your methods will explode in size.
Yeah, so our inline heuristic is mostly based on call frequency. So, yeah.
So, just a general question about Turbofan resource usage. Is it more memory hungry than Crankshaft was, and how is jet time compared?
Both are significantly. I'm not sure about memory, but for sure the time to do a compilation is significantly slower in Turbofan than it was in Crankshaft. But I mean, my portrayal was overly negative. Like Turbofan has lots of benefits. Like it has a much more modular structure, and we do the lowerings in a more rigorous way, stuff like that. So the overall architecture is a bit more heavy, but we also get lots of benefits from it by having a more maintainable compiler and more optimizations. So it depends on the workload, like how important it is to quickly compile. Like for benchmarks, it's kind of okay. Many of them are not that heavy. And in real-world applications, and Turbofan has a strong real-world focus, it depends, but we can compile a lot more. This is also the biggest benefit, perhaps, of Turbofan. Like Crankshaft was very focused. And as soon as it saw anything it didn't understand, it wouldn't optimize at all. Like Turbofan supports all JavaScript functions. We can optimize everything now.
Can you talk a little bit about Ignition as well? What's new there?
Ignition, well, first of all, it's an interpreter. Before Ignition, we used to have full code gen. So the original V8, when it first came out, it didn't have an optimizing compiler. And the only thing it did was it took a JavaScript function and then compiled it to machine code directly in a very simple way, like as a stack machine. And then it would do a lot of binary code patching and inline caches to get performance. So whenever you have a field access, the old V8 would actually insert machine code for the optimized for the case it saw before in the inline cache. The inline cache would actually be bits of machine code inside of the current compilation, and then it would patch that to update for changes. It would generate a lot of code, like a lot of machine code. And so the main reason why we switched to an interpreter was to save memory, because the old V8 really created a lot of machine code, and especially on mobile this was a problem. So our interpreter now is a bytecode interpreter, and the bytecode is much more compact than the machine code used to be. And also we wanted to get away from this machine code patching for different reasons. But in general, like in our new architecture, the interpreter doesn't do any machine code patching. It keeps track of feedback collection in like purely database data structures, and we incrementally replaced all of the machine code, and we also created a lot of code stubs, like small snippets of code. Like just for one load side, we would compile a small piece of code to execute this load faster. And we replaced all of that with data-driven generic implementations, almost all of that. I think that's the biggest change in the architecture.
That presumably comes with a significant performance hit for executing the code until it's compiled.
Yes, full code gen used to be faster than Ignition, but overall the new architecture performs much better now than the old one, because we can compile everything. And as long as we compile fast enough. Yes.
It was interesting in the talk to hear about compilation speed being a primary goal, in the sense that when I consider as an application user, as someone who uses the internet, the sites that, as far as I can tell, require the heaviest JavaScript usage are the pages that I tend to stay on for a long time. So, for instance, Facebook or Slack or something, especially Slack. Have you given much thought to sort of this dual workload, in the sense where, like, some JavaScripts, I'm on a page for 20 seconds and I tab off somewhere else, or pages that are like perennially open in a tab?
Yeah. So the question was, if we focus on compilation speed, like on long-running applications, and I think we focus on both, because also we have like Node.js, which is like really long-running, and then there are long-running web apps, but also like startup is really important to us. You want to use the application right away, and nowadays people ship really big amounts of JavaScript just to show the first page. So this is not a big advantage of the interpreter, that it can kind of start right away. You don't need high performance execution just to display the page usually, but what you need is execute at all. And this is not a benefit of this interpreter approach.
Have you considered pushing profile information from like AMP into Chrome, or something that's like served from Google servers to individual browsers, in order to sort of help the other half of the equation?
Like help in which sense?
So AMP is this sort of will statically create the page and then send it over the wire. It's supposed to be faster.
Yeah.
Is there any interest in doing something like that for code that's executed on the client side?
So the question was if if we do some server-side AMP-like thing to speed up code execution, and I guess we can't really. Like, there's the request of shipping bytecode, which has come up a few times. We don't ship bytecode for a variety of reasons, including that our bytecode is not really portable, and also, like, it's not standardized, and we couldn't change it anymore. And yeah, so I guess for this to happen, there would need.
Questions? Otherwise, we have, I think, it's an hour-long break. I'm not sure why the schedule looks like that, but I encourage you to hang out and talk about VM internals.
So this is not the lunch break, it's just the
No,
hour-long
no.
break. Okay.
I asked Matthias why it ended up like this, but I couldn't get a satisfactory answer.